Today, we are very happy that we can eventually meet you guys, and we will have 3 talks from 4 speakers today. So the first talk we have would be from Timeplus. It's about Proton. It's a very interesting, project which is trying to do the stream and batch unification. And after that, we will have a talk from LinkedIn, navigating automatic scaling in pub subsystem. And afterwards, we have our last talk from FA, talking about how to handle growing Kafka scale at LinkedIn.
Hey, hello, everyone. Good evening. Yeah, my name is Ting Wang, co-founder and CEO of Timeplus. So my colleague, Ken Chen, is chief architect, co-founder. First of all, thank you for linking invitation to be here. So give an introduction with very exciting technology, the product we call the Proton. The highlight is single binary, but it's just we can go through those kind of the background, why we started the project, what kind of use case. And today is also very developer focused. So we really want to deep dive for the technology, see what's going on, what's inside. And also, I know a lot of Flink community here. So we're actually a lot of the, something very interesting related to Flink, just we can compare difference or, very unique things. Very quick introduction about the team. So for me, I previously working for Splunk, almost 60 years there. So Ken is also working for Splunk. It's pretty much like an ex-Splunk guy. So Splunk is for log analytics. So operation analytic. So you can consider that's kind of a subset for the data streaming data. We have the chief growth officer from the KDB. Probably you guys know the KDB for financial trading, or typical stream base. So it's a lot of the interesting streaming use case in financial industry. So we also have COO, the William Plummer. Yeah, actually he's today. We pretty much is 2 years the startup company in Silicon Valley, in Santa Clara. So that's the whole team. So I just back to the background. I think we particularly oversaw this kind of a trend for the data streaming. It's kind of become mainstream. So even for log analytics, we saw a lot of customer consolidate data in the Kafka, Pulsar, a lot of the in there. But how to processing data, analyze data, certainly is a very interesting question. How to enable that? It's kind of motivation when we go back to the industry. From our perspective, what kind of the technology involvement to tackle this kind of the streaming problem. So we actually pretty much put it at a different stage. I think phase 1 is kind of back to the 2000. Yeah, it's more likely how handle a database. How to, for the long time, the query, how just handle, continuous query, how to get it resolved. So it's pretty much like a database technology at that time. And the second generation, need to think like a Flink, a Kafka, those kind of streaming event technology. It's more handle it's a out of order event processing, CEP, a lot of technology at that time. It's pretty much for event processing. So we actually put a lot of paper underneath, just a lot of the academic progress innovation there. So we consider a third generation. When we focus on database, okay, I can do quickly aggregation. When we focus on event, we can focus on event order, a lot of things. So event specific logic. But for some time, for analytic perspective, when I back to my Splunk career at that time, for a lot of log analytics, you have to do the both. Yeah, you need to know exactly a continuous event, but sometimes you have to correlate the historical data. But what about the one platform, how to solve the problem? Looking today, I still the modern data stack still really a lot of different stack, right? So the streaming and also OLAP or a lot of different things, how to different query language, different semantic. So that's what we're back to very high level motivation. So first of all, it should be very dramatic to reduce the complexity. So how enable our data team to use the product, easily. So I think a lot of it, we talk about later, like a SQL, streaming SQL, how to simplify. You don't have to write a bunch of code. Right? The second thing, just really highlight today, just how enable streaming historic, those kind of analytic in the one single platform. So it's just also with one semantic query language. So I think that's a second, most important thing we can talk about today. Third item, just I think a developer always loves the high performance. So how to keep the very fast, high performance, like a query time and low latency, and also like EPS, like throughput, as definitely is our goal. And also how keep the lightweight. We really want to like single binary, very lightweight. It just can run everywhere, like from the edge side and also for the cloud. So that's something our third, motivation here. So that's actually the encouraging. Yeah, if you guys get a chance, just can try the product. We actually, based on the three motivation, we use a single binary. So you can use a very simple command like a curl, just like a 300 megabytes. So you can download the library, you can quickly to analyze the data. And the performance is pretty amazing. So it's just like we can give like a single like a millisecond latency, and also the throughput is pretty high. And also, I think we can deep dive for some details. The last one, just unify the SQL analytic. So I know the streaming analytic, right? The SQL query is not really finalized the standard. So, but we still try to pilot those semantic to query language. I think it's really like dramatically to reduce the complexity. And also, there's a couple of use cases for our experience when we have fortune to walk into a couple of very large scale mission critical application with a couple of big companies. The first of all, we want to introduce like real-time trading monitoring. Trading is all time is matter, right? The data is always the streaming data. The capital market data, just like, for example, like here, like 3,000 stocks, trading account, they just every second just quickly update to those data. But how to detect those kind of like a trading signal, how to like do like a market making, how to like do like a risk control for this fast pacing the data. So that's very, very typical streaming use case. Like it's not really for streaming pipeline. The risk compliance guy really want to get insight. They have to analyze, get alert as quick as possible. So that's something really different compared to like traditional pipeline. That's the second case for the like electrical vehicle like security monitoring. So you see it's a very different, it's based on Kafka, but the data is huge. For the edge side, almost like 50 million EPS. And for the second tier, that dramatically say they need to detect some kind of events, aggregate events, almost like a 10,000 EPS. So they have to reduce a lot of raw events. They need to detect some alerting, like almost like it's a very small the instant per second. So that's something you have to very hierarchy capability to processing those kind of stream data and read some different alerting. So that's something very critical case for the edge processing. Another is network infrastructure monitoring. Global network provider, just like, okay, based on network data, network flow, I want to detect, for example, like a DDoS attack. That really want to know what happened as early as possible, close to the router, close to the user. So that needs capability to analyze those data. The EPS like 1 million, like spike EPS almost like 5 million or 7 million EPS. They're just like up and down. But you have the capability to handle that. And there was a latency that they need to extremely fast. They have very environment pretty limit. It's just like a single rack, right? Just like a 6 or 8 core, and also like a 12 gigabyte memory, something like that. It's really like very minimal the resource. You don't have capability. Say I need a huge cluster. But for centralized, they have very pretty good, for clustering environment to handle that. So that's our solution. Just like, okay, we can put a very single binary for this edge side. They can connect those data and processing the data as quick as possible. At the same time, they can send to the global SOC center to connect those aggregate data. So that's another like edge case for Timeplus. That's it. So it's just for the use case. We can maybe talk offline. But I can try to introduce what's the inside, how to make that happen. So I hand over to Ken.
Yeah, thank you, Ting. My name is Ken Chen, by the way. Yeah, so next I cover what is Proton. Proton is basically single engine which powers Timeplus product. Basically, Proton is a lightweight streaming SQL engine, which is powered by ClickHouse. So basically, we fork ClickHouse code base and start from there. And it tries to resolve one typical problem, which is when real-time data arrives at scale, how can we answer users' inquiry immediately at scale? So it fundamentally is trying to, put an analogy, is basically internally, technically, Proton is basically equal a lightweight solution to Flink, Kafka, and ClickHouse. So folks will basically say, are you guys insane? So because this is a huge monster three top open source projects. Technically, yes, we are insane. From product point of view, no, we are not trying to replace Kafka. We are not trying to replace ClickHouse. We are trying to combine them to provide a very unified solution, and which is more lightweight and simplification. And regarding the efficiency. So what does that mean? So we have a couple of slides in detail how we tackle this kind of problem. So Proton is basically stands on the giant shoulder. So for example, there's a lot of good stuff from Kafka. We have learned a lot of stuff from there. And there's a lot of good stuff from Flink. For sure, we have learned some of the techniques from there as well. So ClickHouse for sure. So we are based on ClickHouse, and we are still focusing on streaming processing, streaming analytics, but dedicate the historical query processing to ClickHouse. ClickHouse is very, very good at historical query processing. So internally, Proton at a high level, it has TCP, HTTP in input format. And in the middle, at a high level, it has stream store. And this is something we built from scratch. We have a historical storage, which is based on ClickHouse. And on that, we have stream append-only stream. We have changelog stream. We have version KB stream. And we have unified processing for sure. And we can query on external stream. For example, we can query on external Kafka topic or Rapanda topic in different formats. For example, Aerial format, CSV, JSON, you can name it, a lot of them, because we have inherit a lot of legacy regarding the format from the ClickHouse community. And we can query on file logs as well, or different files, CSV file, JSON file, or what kind of different files, we can support that. We can also send the data to external ClickHouse because we are based on ClickHouse. So this is a very native integration. If our customer already have a ClickHouse in-house, they do not need to move the data around. Yeah, so if we dive into the storage a little bit, so when a stream gets created, basically a stream has two parts, the real-time parts and the historic parts at the storage layer. This is the bottom layer in the diagram. So when the data basically get ingested, appended to the stream store. Stream store, internally we call distributed replicated NativeLog. It is append only. Some of the fundamental technology is basically borrowed from Kafka. Kafka is append only, right? But the replication is our replication is not is using a different distributed algorithm, which is multi-route. And also when the data append to the replicated NativeLog, when it is committed, in the meanwhile, in the background, we have different threads basically consume the data, committed data in the NativeLog, write the data in batch to the historic data store. So, and from the user's perspective, they do not need to worry about the internal details. So, for example, when user issue a query, and internally we can try to, what's the data? Where's the data I need to look at? Some of the data may be in the historical store, and some of the data may be in the streaming store. And internally, we can glue them together. If we dive into the streaming store, which is NativeLog, this is fundamentally a replicated write-ahead log, and we borrow a lot of idea from Kafka as well. So, and which is powered by multi-route consensus. One thing I like to mention is that on the file disk, we have built different reverted index. For example, on right in this diagram, we have segment file. And segment file, we have built a inverted index for sequence number to file offset and sequence or timestamp, event timestamp, append timestamp to sequence number. So basically, we build the inverted index for logical timestamp, which is sequence number, and we also build inverted index for the logic physical timestamp for event timestamp and also for append timestamp. This is basically very useful for you if we like to rewind the stream, and we can do fast lookup where I can, for example, if you seek to rewind the stream to a specific timestamp, we can use this inverted index to fast look at where the file we need to look at. That will be a little bit more overwhelming. So in each of the log segment, which we have the log entry. In the log entry, we have a specific file format or data format. So probably I do not have much time to deep dive into each of them, but at a very high level, we have for the data payload and metadata payload, metadata part, the data part. The data part is columnized. Is columnized in columnar format. Columnar format has basically the very good very good nature, which is enable vectorized streaming processing. So vectorized stream processing is super powerful. If we have a batch, for example, if we have 100 events there, if we can use this modern CPU SIMD to do the aggregation, that would be way more fast. And then the other benefit is basically the serialization benefit is the cost is super small. So since that our in-memory representation and on-disk file representation keep basically the same. So you can load the data from the on-disk and then deserialize it to in-memory. That will be really fast. In the data part, there are some of the database technology, which is projection pushdown and the product is pushdown. Projection pushdown is like, I have 10 columns, but I like to only select 2 columns from them. I do not need to worry about the other 8 columns. We can fill a lot of data very soon at the storage layer. Product pushdown is like when we have a timestamp, but we like to query a timestamp, but the timestamp does not meet that the condition. We can fill out the whole log entry very quick. That will be performance will be really good. This streaming syntax is basically we borrow a lot of idea from the one SQL to rule all. That paper, that scientific paper is from Google and written by Tyler Arquette. That paper basically influenced a lot of SQL usage and also data SQL processing semantic. We have based on that paper. But in general, we can do SQL. We can do streaming query processing in the SQL. We can do table query processing in the SQL. We can combine them together. We can do pure table query processing. We can do pure streaming query processing. We can unify them in one SQL as well. Since that we are based on ClickHouse code base, and each of the queries basically constructed to an execution plan. So it's just a DAG. This DAG is super important because it impacts how to do the state checkpointing. So this is basically some everybody do this stuff. The DAG basically we have borrowed a lot of good idea from Flink as well. So state checkpointing is like similar idea. We have basically periodically emit the very special watermark, which is a checkpointing watermark, and the watermark basically flow through the whole DAG. And for that two stateful operator in the DAG, which needs to persist the data. One is the aggregation, and then another is join. Once everything persistent to the query store state store file system, and we can basically finish one round of checkpointing. This kind of mechanism is basically from very similar to Flink. Proton unifies streaming and historical query processing. So when a query travels through from a historic data store to stream data store, basically we do not want data duplication. We do not want data gap. So how do we do that? Basically, every time we commit the data, consume the data from NativeLog and commit the data to a historic data store, basically we commit the sequence ID as well. And when for example, if you have a query, I like to rewind the data, backfill the data 1 day ago, and we basically will pick one day historic data from the historic data store, and then connect the data with real-time data, which is from stream store. So we are using the sequence ID, lots of sequence ID to connect these two pieces together. From any user point of view, it is a very consistent view about the query processing. So historic data store, we can also use the historic data store for the streaming data enrichment lookup, and also we have a lot of use cases like troubleshooting. So streaming is really good at real-time alerting or monitoring. So for example, if there's some CPU high usage, but if you like to do deep dive why the CPU is highest, you need to dig into the raw logs or raw events. So that for this kind of use case, basically historic data store can try me. User can do ad hoc query against the historic data store. So another use case is basically we have a lot of data in historic data store. You like to do real time comparison about a window in historic data store maybe 10 months back, and using 10 months back window to real time compare the window right now. So this is another use cases. There are quite a lot of other possibility. If we control the storage, SQL is not the perfect to handle some of the use cases like state machine processing, which is very stateful, right? You have one input, and you see some events. You basically jump to another state. You jump to another state, and then you have a final state. It's really hard to express this kind of process this kind of use cases by using pure SQL. So we have some use cases user like to do state machine based processing. So we extend this Proton to support JavaScript, user-defined function and user-defined aggregation function. So basically, user can create a user aggregation function, do all kinds of streaming processing. Yeah, and user do not need deployment because our Proton basically embedded V8 engine, JavaScript engine there. Finally, I'd like to do a comparison regarding the user experience between Proton and Flink. This use case is based from one of our community user. Basically, he like to do as of join, but his latency is super strict. As of join, is basically I like to find the closest match. The timestamp need to be nanosecond precision, and I like to do that. We have a equal match, that's fine, but there may be a lot of candidates. In all of the matched candidates, I like to find the best one. This is fundamentally how the as of join does. So this is a financial use case is that he has a very strict latency, join latency, and also throughput. So first of all, they can create a stream, external stream, basically to point to the topic. On the left side and right side, basically similar stuff, pointing to a broker 1992 and topic events. This is the second, create a sync topic. I like to write the data to topic because we have source, we have sync. And then in the middle, we have create a different view, fill out the data. We like to basically these two are basically the same. And also create another view. We like to, this is, the first view is basically the order book. The second view is basically the peak in financial service. And lastly, in Flink, they need to create another view, which is basically fill out the using the partition by order by to get the latest data, latest order book. And in Timeplus, we do not need that. This is the meet. This is the final case. Final case is basically like to join the view, join like to a streaming join. Basically, we have left streaming, we have right streaming. They like to join together and like to do first of all do the equal join, which is basically the tick instrument and BBO instrument. And then we like to do a as of join like sequence. So the sequence is the best match. For this case specifically, the community user basically try Flink out and also Proton out. We have 3x better latency. We have 3x better latency and also 2x memory usage efficiency. And to the best of my knowledge, it looks like Flink does not support nanoseconds timestamp. This is from the community user. Basically, this is what he said, and he needs quite a lot of different workarounds. So lastly, I'd like to do a quick demo, which is another use cases from community users. So like stream aggregation 1 billion events with 130 million unique IP predicts. And so he tried a lot of web vendors, but most of them does not work because of the memory efficiency problem. So because 130 million unique IP fix is a lot. All this basically below the memory. I can do curl command to download the single binary because everything is one single binary. And nothing here, and I can just launch it up. Using Proton client to attach the server and create a stream. And then I can run select. Basically, I create a random stream. So basically, it's randomly generated a lot of unique IPs, and which is basically 130 million unique IPs. And we are processing 1 billion events, and it's already done. This is 134 rows, and it's processed 1 billion events in 15 seconds. Let me run this again because it's real quick. And see the usage here. The usage is basically 8 gigabyte, almost 9 gigabyte, and in 15 minutes we can get that done. Yeah, this is all I have today. Thank you so much. Lastly, basically, Proton is open source. Yeah, if you like to try, give it a try, give it a spin. Yeah, because it's super easy. Just like curl command to install the Proton in your local directory and spin up, and it can do streaming query processing and historical query processing in one single banner. Thank you.